have three different ways to calculate delta H reaction. We have coffee cup calorimetry, we have Hess's law, and we have from delta HF reaction values. I will tell you this, most of the time I have ever calculated delta H reaction, it was from delta HF values. That is the most powerful and perhaps simplest way to do it. So let's cross our fingers and hope that's on our exam, whenever that is. Now, I must say by far the most useful thing from delta H reactions, once we know what a delta H reaction is using it to estimate the amount of energy, the heat energy that comes out of a reaction or goes into it, using stoichiometry. So let's get to that. This is Roman numeral 6. Says, we'll go straight to examples. When 51.2 liters of oxygen at 1 atmosphere and 298 Kelvin are consumed in the burning of propane, how much heat energy is produced? So let's see, I've got my calculator here. So I notice that oxygen is a gas. I've got the volume, pressure, and temperature of that gas, so I can find moles of gas. That's an ideal gas law problem. And from there, I will start the stoichiometry part. So let's write our ideal gas law, personalized for oxygen. I know my atmospheres. I know my volume. I don't know my moles. I know my ideal gas law constant. (0.08206 liter atmospheres per mole Kelvin. And I know my temperature. Solving for the moles of oxygen. I get 2.09 moles. As you know, I always do my ideal gas law separate from my picket fence, my system for doing stoichiometry problems. So I'll take my 2.09 moles. I know that for oxygen, for every 5 moles of oxygen, I get negative 2,044 kilojoules. It's not, remember from a previous lecture outline video, that's minus 2,044 kilojoules per mole of thing with a 1 coefficient like propane. It's 2,044 kilojoules released for 5 moles of oxygen. I think my picket fence is too long because I'm trying to find how much heat energy is produced, and I'm there. That's an equal sign. I get negative 854 kilojoules, and that's just energy. That's an amount of heat energy. That's like a Q. And the negative part tells you that it's produced. Now, for the same reaction, how much energy is produced when 16.4 grams of propane are burned? For this one, we'll start with grams of propane. This one I think we'll need a longer picket fence for. So propane, its molar mass, so 3 times the molar mass of carbon plus 8, we get 44.09 grams of propane per 1 mole. And for every 1 mole of propane, and that is the coefficient, 2,044 kilojoules are produced. That's why it's negative. And so here is our delta H. Here above in the previous example, we had to massage our delta H into that negative 2,044 kilojoules per 5 moles. Well, now let's multiply this out. And this time I get minus 760 kilojoules. It is just kilojoules because all my other units cancel out. Let's do another one. This one is calculate the heat released for decomposing 10.0 grams of limestone calcium carbonate. In this particular one, very typical problem. You have to calculate delta H reaction from delta HF values and then use that for stoichiometry. My system for doing that is to write the delta HF values underneath each of them. So calcium carbonate, calcium oxide, oxygen is 0. Now calculate delta H reaction. That's going to be products minus reactants, accounting for coefficients, which are all 1s in this problem. So applying the formula for delta H reaction from a previous video, we've got minus 1 times the delta HF for the products, minus the reactants, times 1, and we'll omit the math for the 1s. We have a minus here, so that's a plus. 572.7. Kilojoules per mole, highly endothermic reaction. Takes a lot of energy to get this to go. And let's see, so now we have 10.0 grams of limestone. Got my periodic table right here. I need to know that calcium's 40.08. Carbon plus 3 times oxygen, 100.09. Then for every 1 mole of calcium carbonate, it takes 572.7 kilojoules of energy that are taken in. $57.2 kilojoules. It says heat released in the initial problem. This is heat absorbed. Because it is positive, which means it is taken in. This is an endothermic reaction, absorbed. Or taken in. The positive number tells you that anyway. Let's see what we got left. One more companion problem. Look for the answer to that posted online. And this is the end of lecture outline number 7.